Alright, so in this video we're looking at exact differential equations. Now in my opinion, exact differential equations are a lot of fun. I mean, at first it's a little hard excuse me, to learn the way it goes, but once you get it down, it's super simple. Now, if you've taken Calc 3 before, you might recognize this. When I took Calc 3, when we were dealing with potential equations with, let me think about this, with the fundamental theorem of calculus for line integrals, right? When you're able to use the fundamental theorem of calculus for line integrals and find little f, right, to integrate across from one point to one point. So if you remember that from line integrals from Calc 3, it's the same exact process to find your little f, that function. It's the same exact process. They just used, like, I know in my textbook at least, in Calc 3, it was different notation. The notation in my differential equations textbook is very fancy. And I'll show you what I mean in a second, how my book's notation is. So an exact equation is as follows. We're going to have some n, or I'll write it this way, some m. Let me increase the size of this pencil. We have n of xy times y prime plus m of xy times, that's it, is equal to 0. So this is the exact form. This is the form for exact equations. So it is exact. So we don't actually know if this particular form is exact or not. The only way we know, now if you took Calc 3, you might recognize it's basically, if in Calc 3 you remember you had a test if it was conservative, if it was conservative or not. In this case, we're testing if it's exact. It's the exact same process. Exact same process, get it? Right, exact if there exists a function phi, capital phi. My textbook uses capital phi as a function of xy. So if you take in Calc 3, you remember you solve these equations and you get a function, right? And that was our answer. So that's what we're solving for. We want to solve for phi. Let me move this. So we want to solve for phi, right? So now, you're also going to might recognize this from Calc 3, but so n from the top here, this n is the same thing. I'm just going to rewrite it down here. N is actually equal to the partial of phi with respect to y, while m is equal to the partial of phi with respect to x. So you can also write this in different ways. So I'll do or. You can say n is equal to I with respect to y, and m is equal to, phi, not I, phi sub x, right? That's the same notation. It's just different notation. If you've taken Calc 3 and you've taken partial you know how to do partials and stuff, this stuff should be very familiar with you. So now, okay, yes, to test if it's exact. So, is it exact? Well, the way to know if it's exact, excuse me, if m sub y, well, and with respect to x, partial of n with respect to x, then the equation is exact. Let me spell this out. And the equation is exact. Okay. So I say this might not make any sense at the moment, but it will in 2 seconds when I'm going to go through a bunch of examples in this video. I think I need to add a page here. Hold on. I think for exact, it's just a matter of... what is this? Oh, I have a little pointer thing. I think for exact, it's more important to just rep through a bunch of problems. That's the best way to learn how to do these ones. So it's very every question is very repetitive in the method. So it's not like you're doing anything crazy. It's kind of similar to like separable and integrating factors. You do the same thing every time, but with these questions, it's a little bit longer of a process. But it's still very you pretty much do the same thing every time. So let's just go through a whole bunch of them to get it down. So now if we're looking at this, if you look back up to our form here, we have n times y prime and plus m. So this, let me rewrite this. So we have 2x plus 3. This would be our m, right? This is our m plus 2y minus 2. That's our n. Y prime is equal to 0. Excuse me. Okay, so the first thing we want to do is we need to test if it's exact. Okay? Well, first thing, let's do this. Remember that m is equal to partial phi with respect to x. So that tells us that the partial of phi with respect to x is equal to 2x plus 3. And writing this down at first is helpful at first. But after a while, once you get good at these, you can kind of just skip this step and just know this, like keep this in your head. I'm sorry, 2y minus 2. And just kind of keep this in your head, because you're just writing this down now, you're going to use this information later, and I'll show you how we'll use it. So now we can test if it's exact. So now remember, for exact, the partial of m with respect to y has to equal the partial of n with respect to x. So let's do the partial of m with respect to y. This is the same thing as writing my, right? That's equal to 0, right? Because there's no y term in m. It's just 0, right? Same thing for n, actually, with respect to x. It's equal to n sub x, which is equal to, once again, we have no x in our n. No x term, so it's just 0. So guess what? M sub y is equal to n sub x, which is equal to 0. So that tells us that it's exact. So that answers part A, right? It wants us to determine if it's exact and then find the solution. So now we can find the solution. Excuse me. So now you have two options here. Whichever one. So my suggestion to you is you look at m and n. Whichever one you think is easier to integrate, that's the one you're going to pick to use first. Now in this case, they both are pretty much the same difficulty in integration. So I'm going to pick the m term, okay? Now we know that, like I wrote down here, I should have wrote this down here. M is equal to and n is equal to, right? So we know m is equal to partial of phi with respect to x. So what I'm going to do, so we know that this is our m, right? And this is this. So I'm going to pick m first, or the partial of phi with respect to x. So the partial of phi with respect to x is equal to 2x plus 3, right? Now, you'll notice here, all we have to do is integrate. So if we integrate the left side, that just becomes phi. And the right side will become x squared plus 3x, right? Okay, so now we're also going to have a constant here. But because this is actually, you can think of it like a partial integral. We're integrating with respect to x. See, in these problems here, we're going to have n and m's that are going to have x and y in them. So like when we have the integral of x and y, we're only going to take the one. Like I'll show you it in the next example. This example is pretty straightforward. Yeah, but the next question we're going to do is going to have both of them. And you'll see that what I mean. But for now, just integrate it like you always would. So now that we have this, we're going to have plus some constant, but it's going to be with respect to y. Right? Because it's a function of y. Because we just integrated with respect to x and not y. Okay? So now that we have this, now that we have phi, well, what about, hold on a minute. I'm noticing a mistake here. N is with partial of phi with respect to y. Sorry. Oh, and then I have it backwards down here too. Oh no, it's good down here. We're good. Sorry about that. We're good. Small mistake I made. Yeah, what about, as I was saying, what about the partial of phi with respect to y? Well, now we can take the partial of phi with respect to y. Let me show you this cool trick here. So now we take phi and we take the partial of phi with respect to y. So this first term becomes 0. The second term becomes 0, right? Because we have no y in those terms. And this is just plus h prime of y, right? Now we're going to set this equal. We're going to set this equal to this right here, because we know that this partial phi with respect to y is equal to 2y minus 2, right? So this is also equal to this. So it tells us that h prime of y is also equal to 2y minus 2. So now we can rewrite this. We can just focus on this right here. So we have h prime of y is equal to 2y minus 2. Okay, I'm going to need another page here, actually. Okay, so now we can integrate both sides, because we want to get h of y, not h prime of y. So okay, and this is with respect to y, by the way. So h of y equals, integral of this with respect to y would be y squared minus 2y plus now it's just going to be a c. Excuse me. All right, now it's just going to be a plus c, because we already yeah, now it's just going to be a plus c, because we already used the h of y. Yeah. Okay, so now we have h of y here. We can plug it back in up here, and for phi up here, we can plug it back into here. So we have x squared plus 3x plus y squared minus 2y plus c is equal to 0. Okay, we set phi equal to 0. And yeah, in these equations, if you took Calc 3 before, you would have still had that phi there, right? And you set it equal to phi. But for these questions, we kind of disregard phi at this point, and we just set it equal to 0, the right side of this equation up here. So anyways, now that we're here, for these questions, it's more common that you're gonna solve for C now. Wait. Okay, so I just noticed something. I think I'm noticing a difference here between Calc 3 and this class. I actually took Calc 3 after differential equations, so I'm used to doing it like the Calc 3 way. It appears that the textbook and what I used to do is you don't actually write that plus C there for some reason. I don't remember why that is. But I know that you end up with equals C down here. So I know that C comes from somewhere. I'm thinking it comes from there. The book just kind of skips over that. I'm a little confused right now. But maybe that's where that C comes from. That's my guess. It has to be. I mean, you do get a constant from that equation. I mean, that has to be where it's from. That's what I would assume. I don't know, maybe you guys know. But anyways, this is the solution to this problem. Now let's look at the next one. The next one's a little bit more fun. The next one's a good example. So this one, we have 3x squared minus 2xy plus 2 plus 6y squared minus x squared plus 3 times y prime is equal to 0. So this looks a little more complicated, but it's really not that bad. It's not that bad. So which one's n, which one's y again? Okay, so yeah, this one's m. This one's n. Let me do that in green. This is a partial of phi with respect to x, right? Is equal to mx, which is equal to 3x squared minus 2xy plus 2. The partial of phi with respect to y is equal to 6y squared minus x squared plus 3. So now, first things first, is it exact? Well, let's see. So remember, my has to equal nx. So my is equal to, so m with respect to y. The first term, 3x squared, 0. We have no y in that term. The second term, 2xy, with respect to y, will leave us with just minus 2x. And the last term, there's no y in it, so 2 just disappears. nx. 6y squared, we have no x term there, 0. Minus x squared, that becomes minus 2x. The last term has no x in it, so 0. And look at that. M of y is equal to n of x, which is equal to minus 2x. So it is, in fact, exact. So now we need to find the general solution, right? Also, I don't know if I mentioned this before, but the solution to a differential equation is called a general solution. All right, that's a general solution. So now let's find our general solution for this problem. So remember, like before, you can start with phi, whichever one you want to integrate first. Let's choose, just to show you that you can do either one, let's do partial of phi with respect to y first. So let's start with this one. Okay, let's start with this one. So we have 6y squared minus x squared plus 3. Let's integrate both sides. Now this is with respect to y. So you'll see how, remember I said in the last problem you have to integrate with respect to y? So this is a little trickier. So this will become 6y cubed over 3, which is just 2y squared, 2y cubed, minus, and you see now, this x squared isn't going to disappear. It's not like you taking the derivative of it. It doesn't become 0. When you integrate with respect to y, like an x function, you treat it as a coefficient. So this would be, so think of it as any other coefficient, like how you've always integrated, and that's just times y. Same thing for this last term, 3 times y. Right? And now for this one, because we integrate with respect to y, our constant is going to be a function of x. So now we need to solve for that function of x. So we know we did it with respect to y, so now we have to do phi with respect to x. Partial phi with respect to x. And that would be, now this first term would become 0, minus, that's 2x times y plus 0 plus h prime of x is equal to, what did partial phi with respect to x from before was 3x squared minus 2xy plus 2, right? So we're left with this. So then we integrate both sides. And this one's with respect to x, right? Yep. So this would be h of x is equal to, that 3 will cancel, right? And then we're just left with x cubed minus 2. That y is going to act as a coefficient. So this would be 2x squared over 2. 2's cancel. X squared times y plus 2 acts as a coefficient, x. Now, I need another page again. Now we have h of x. We plug that back into phi. So, wait, I just noticed a mistake. Oh my god. In this previous step up here, I completely forgot about this term over here. Those actually cancel, so this is actually easier than it looks. So if anyone saw that mistake, that's good. If you've seen it, see, I was just simply testing you. Yeah, now plus 2 is still there. Okay, so now this is what we're actually dealing with. So it's a little bit more simple, right? Now we plug that in for phi. We have 2y cubed minus x squared y plus 3y plus x cubed plus 2x, right? Now once again, that c comes out of nowhere. I'm not entirely sure. I'm not entirely sure. You're gonna set this equal to yeah, get rid of that phi there and just set it equal to c. Right, I'm not entirely sure where that c comes from. I'm assuming it comes from this here. And when you subtract the c over, that becomes a new constant, right? Whatever. You know. And it'll become just c. Because negative c is equal to a new constant, right? Just c. I guess that's the same thing. That's what I would assume. Like if it's plus c, then if that moves over and becomes minus c, that just becomes a new constant. That's what I would assume. I hope that's right. Anyways, this is the correct answer for this problem. See, not too bad so far. Once you get the hang of it, it's pretty straightforward. Just remember that you have a lot of options here. You can either choose, to use the d phi dx or d phi dy to start out with to integrate. But after that, it's pretty simple, pretty straightforward. Okay, let's look at number 5. So this one, it gives us in the form, it gives us it gives it in a different form, right? So we can immediately rewrite this. This left side can be rewritten. This left side can be rewritten as y prime negative ax minus by over, and don't be afraid of these letters here. This is a very simple problem. Don't be fooled. Don't be fooled. So if we rewrite this, this will become minus a. Okay, let me do this first. Bx minus cy times y prime is equal to minus by, right? So now if I move that right side over, we have ax plus by plus bx minus cy times y prime is equal to 0. So this is our m. This is our n. So that tells us that d phi dx is equal to ax plus by, and our d phi dy is equal to bx minus cy. Now, is it exact? Well, let's find out. So, remember, the partial of n with respect to y has to equal the partial of n with respect to x. So, my, the first term, ax, 0, right? We have no y term there. The second term, we have a y. So, the derivative of by with respect to y is just b. Now, n. Some of you probably already see the answer here, right? The first term actually, I have made a mistake. I wrote the problem down wrong. I did not see that negative out front right there. Oh my god. Well, anyways, with that negative being out front, oh, I see what I did. I accidentally wrote it up there. That just flips the signs in the numerator, right? So then this will become minus ax plus by. We move those over. That becomes positive ax minus by. Yeah, and then now that's correct. Okay. No wonder why, because I knew the answer, and it wasn't working out, so I knew something was wrong. Yeah, okay, now we're good. Now we're good. So m with respect to y is actually going to be negative b, and n with respect to x be positive b. So my does not equal nx. So then the answer, well, then the problem's not exact. So right there and then, we're done. That's it. Problem's not exact. We cannot find a phi then. All right, so then that's it. Not exact. Number 7. So for number 7, let's just go through this one really quickly. Try this one by yourself and I'll do it. So now we have y over x. I'll just write it up here. So this is our m, this is our n. Our d phi dx is equal to y over x plus 6x. Our d phi dy is equal to natural log of x minus 2. My is equal to 1 over x, right? And our nx is equal to 1 over x. So then they're equal, so then this is exact. Okay, so now I'm going to pick which one I prefer to integrate. I'll just do partial phi with respect to x first. So I integrate both sides. This becomes phi is equal to This is with respect to x, right? So the y just becomes a coefficient, right? So then we're left with y natural log of x, absolute value this time, plus 3x squared, right? Plus h of y. Now, we used x already, so now we're going to use d phi with respect to y. So that would be, the y would just disappear. We're left with natural log of x plus, that would be 0, plus h prime of y is equal to, we look back up here, d phi dy is equal to ln of x minus 2. Okay, now this cancels with this. So then we're left with h prime of y is equal to negative 2. Integrate both sides. H of y is equal to, with respect to y, is equal to negative 2y. Now I'm going to go on and assume that this is plus c here, that plus c is there. I hope so. I hope that's how it goes, because I'm confused why my textbook just doesn't show that. They literally just don't include this plus c here. So I don't know. That has to be where it comes from, though. I see no other way. Okay, so we have the minus 2x plus c. So we have h of y. Let's go ahead and plug it back into phi up here. So we have y natural log of x, absolute value, don't forget that, plus 3x squared plus h of y, which is minus 2y plus c, equals 0. I'm going to move that c over. It's going to become a new constant because it's negative. Okay? And that's our solution. Okay, I believe I have 1 and 2 more problems here. Yeah, so now this next one is an IVP. So it's a little bit different, but this time, instead of, we're not going to have a c in our answer because we're going to be able to actually solve for it. So once again, our m. Now I'm going to skip the whole d phi di thing, d phi dx thing, because you should know by now which one is which, right? We don't have to go write that down every single time. So I'm going to kind of glance over that one. But we know that our m is this and our n is this, right? So then, let's test. M of y is equal to negative 1, right? N of x is equal to negative 1. So it's exact. Now remember, we could pick either one we want to do. Either d phi dx or d phi dy. Remember, this is d phi dx, this is d phi dy. I don't think it matters for this one, right? So let's just do x. Why not? So d phi dx is equal to 2x minus y. Integrate both sides. Phi is equal to, with respect to x, of course, x squared minus y times x, right? Y acts as a coefficient. Plus h of y. Now, we do it with respect to y. This becomes 0. This becomes x. This becomes h prime of y. Set that equal to d phi dy, which is this up here, 2y minus x. Very lucky. The minus x's cancel. We're left with h prime of y is equal to 2y. Integrate both sides. H of y is equal to y squared, right? Plus c, I guess. So then we're left with x. Well, let's look at back of our phi. X squared minus y times x plus y squared is equal to c, right? So before, this would have been our final solution, but we're given y of 1 is equal to 3. So that tells us that y is equal to 3 and x is equal to 1. So, excuse me. Wait. All right, yeah, so 1 squared minus y is 3 times 1 plus 3 squared is equal to c. Well, that's just 1 minus 3 plus 9. 9 minus 3 is 6 plus 1 is 7. So now we can just plug that back in. Right? Now this is our answer right here. That is our general solution. Okay. We have one more problem. This one's a fun one. So at first, when I first looked at this, I remember when like a year ago when I was doing this question, I looked at it and I skipped it because I was like, oh, I don't know I wasn't really too good at this stuff yet, and I was just like, I'm not gonna have to know how to do that one. And then I looked at it again, and honestly, it looked really easy, and it is really easy. So it's just a cool little alteration of what we've been doing. So we're given this, and and it's not going to be exact. We're gonna find, so we just have to find what value of b would make it exact. It's just a different way of thinking of it. So once again, let me see here. Yeah, this is our n. I always forget which one's n and which one's m. I haven't done this in a while. So that's our n, that's our m. All right. So first things first, I noticed that our n is undistributed. Blah. So we have to distribute that x squared into there. So this is xy squared plus bx squared y plus x cubed plus x squared y times y prime, right? So let's now find our my. My would be 2xy plus bx squared, and x would be 3x squared plus 2xy. Okay, so looking at this, these two terms are the same. These two terms are not. So what value of b would make these the same? 3, right? That's all it wants us to do here. It's really straightforward. So it just wants us to find the value of b that would make it exact, which is 3. So now we can just use this value now and rewrite our equation, because now we know it's going to be exact. If this is 3 right here, we know that this is going to work, and it is exact. Right? We just proved it. Okay, so now we can go ahead and find our general solution. So I'll start with y this time. Why not? d phi dy is equal to integral x cubed plus, and once you get good enough, you can just honestly skip out writing all this stuff out and just go right to the steps, you know. But it's just good to practice to start out with. This is dx, not dy. So we're left with phi is equal to, with respect to y, this just becomes x cubed y plus x squared y squared over 2 plus h of x. Now, d phi with respect to x. This would be 3x squared y plus 2. 2's will cancel, right? X y squared plus h prime of x. That's an x is equal to Remember, which one's with respect to x? M, right? So this is our phi with respect to x over here. This was our y. Xy squared. Okay, I have it right here. Xy squared plus 3x squared y. And does anything cancel out? Yep. This cancels. Oh, very nice. They both cancel. And we're left with h prime of x is equal to 0. So that tells us, right? Oh my god, dx. Right? So now, plug that back in here. X cubed y plus x squared y squared over 2 plus c is equal to 0. This can be rewritten. Now my textbook multiplies both sides by 2, so they rewrite it like this. They get rid of the fraction. Now this right here becomes a new constant, right? So that's 2x squared y plus x squared y squared is equal to c. So this is our general solution for this problem, right? Okay, so this is exact equation. This was a bit longer of a video than I expected, but when it comes to these problems, just a lot of practice works is the best method to get used to how to do these. And once again, if you had fundamental theorem of calculus for line integrals in Calc 3, it's the same exact thing, just different notation, different purpose, I guess you would say. Instead of exact, it was conservative, right? If the field was conservative, you had a test if the field was conservative. It's the same exact test though. Same process. Alright, so I hope you enjoyed this video. In the next one, we're going to look at what happens if the exact equation, if it's in the form of an exact equation, but it's not exact, right? There's actually a way to make it exact with integrating factors, and I'll show that in the next video.